Swayam Prabha. Digital India. Educated India.
Okay. So, the last class and the class before that, we were looking at or we are beginning to look at the force development. Right. So, that is what we were looking at. It was very clear from a very simple analysis of our free rolling that force development depends upon the deformations in the tread blocks. When we say tread, it includes belt. It's a very loose term that we are using. Okay. So, in other words, all that stiffness in the longitudinal direction put together, we call that as a tread or a tread block here. Right. Yes, stiffness of the tread is very, very important. You saw what's a tread. That's a tread. Even if it's continuous, it doesn't matter. It doesn't matter because we can assume that as if it consists of a number of what we called as bristles. Okay, we represented these treads by means of bristles. It doesn't matter that even if it's a continuous piece. Incidentally, there were some questions in the last class, at the end of the last class. Please note that this is the cut section of a tire, right? It's a cut section of the tire, right? And that section, when you expand it, it becomes the tire, right? It's big. One of the questions is it's big. It looks very different from what we see in the cars. Yes, this is not a passenger car tire. It's a truck tire, right? What we are talking about is a truck tire. Passenger car tires are much smaller. Maybe in the next class we will get the passenger car radial tires. One of the key things that you would have noticed is what is called as the aspect ratio, and we will look at the aspect ratio effect on rolling resistance shortly. So, the aspect ratio, what we mean by aspect ratio, the height to width the ratio, right. So, this is typically of the order of 50% in the passenger car tires. It can be 45. When you go below, you can also go up to 35, 30. Then you call these tires as low aspect ratio tires. These are almost 1. So, these tires aspect ratios are much bigger. That these tires, in sense, these truck tire aspect ratios are much bigger. Okay. So, that's one of the things that I wanted to say. The other question that was asked is between this what we called as a rib tire and the lug tire. Okay. What is this front axle, rear axle, and so on? I skirted it a bit because I wanted to finish this topic, and you may understand it more as we go along, especially when we talk about stability and so on. Since there was a question yesterday, so I would answer that question with in such a fashion that with your knowledge right now, you will be able to understand the answers. Lug tires, or I would say grip tires, they have grip. They have what is called grip, and hence they are supposed to be used in the rear. Okay. Now, what is grip? Why is that the lug tire has grip? Does it really have a grip? Okay. And what is it that gives this grip, and so on? Okay. Now, this is a question which you have to answer very carefully. If you go to most of the websites of the tire manufacturers, they would call this rib tire to be the steer axle tires. They would recommend that you can use this in steer axle, and many of them would recommend that these lug tires are used in the drive axle. Okay, this is what they would recommend. Okay. Is there a difference between the two is the first question. They would also add some things like this. Rib tires have steering stability. They would use the word stability. Steering stability is what they would use. Okay. And correspondingly, they would suggest that the lug tires are high grip, wet grip tires. Okay. Many of them would say it has a good wet grip. All of them, okay, these statements, all these statements, and then there would be tires which I called as hybrid, which they would call as all-wheel tires, and so on. All of them should be taken with a caveat with the rider. Basically, the most important thing here is this wet grip with a lug tire. Because of the fact that there are channels, if you look at a lug tire, you would see a number of lateral channels for taking or removing water, okay, as it goes along. What is called as hydroplaning is avoided, okay, in this kind of lug tire. Hydroplaning here I am using in the sense that there would be a water film that is formed and the friction coefficient reduces and so on, which we will see again in the next couple of classes. Okay. So, there are channels for the water to be carried, and hence the grip is enhanced by that process, and hence you would say wet grip is high. Strictly speaking, dry grip is not necessarily higher than a rib tire. In fact, many experiments show that rib tires have good dry grip. Dry grip in the sense that when there is no water, okay, no fine sand and so on, okay, then we say that we have a dry grip, and the dry grip is actually better in a rib tire because you have a lot more rubber that is sitting on the road. Okay. Strictly speaking, that's the case. So now there is a lot of research going on, and there are tires where you have a rib-like tire with a lateral groove in order to carry this water and so on. The grooves are very strategically put. There, a lot of analysis is done. There's a fluid structure interaction analysis done, okay, in order to understand how the water flows. These grooves are put so that the water is carried. Clear? Usually the rib tires, there's no rule, okay. I'm talking about the usual practice, okay. Usually rib tires have lesser, what is called as the non-skid depth. This is called as NSD, non-skid depth. Non-skid depth is this depth, okay, this depth which is in the groove. This is the non-skid depth, right? Do you understand that? That is the non-skid depth. So the non-skid depth, okay, or NSD as it is called, is usually for a rib tire lower than that of the lug tire. Okay, this is usual practice. It is lower. In other words, again, under most instances, the rib tires have much less rubber mass when compared to the lug tire. Okay. Basically, because of the fact that this is being used in drive axle, because of the fact that the wear rates are higher, they use it in the and they want it for a higher mileage, and they use a lot more rubber there. Because of the fact that these tires have less rubber, okay, and because of this kind of this construction, usually the rib tires have much or less rolling resistance, and the noise characteristics are much better, much better. Rolling resistance is slightly, here and there. You cannot make a statement out of it. Why I am being very careful in making these statements is because all these statements, okay, are maybe in variance when you have different non-skid depths. In other words, you have to compare apples and apples. If one tire is worn out more and the other tire is not worn out, then these sentences are not valid, and so on. So you have to be very careful in these sentences, okay, and hence all these things you have to understand it with that theoretical background. Clear? As far as the noise is concerned, again, the rib tires have much better noise characteristics when compared to the lug tire. I won't have, that's another course, I won't be able to go into the noise aspects, okay. But nevertheless, just understand that the noise levels of a lug tire is much higher than the rib tire. The decibel scale can be as high as 4 to 5 dB. Yes?
What do you mean by the noise here? Noise is what?
Okay, what is noise? What do I mean by noise? Obviously, all of us, have you stood near a truck? Do you hear the noise as it goes, okay, past you? Now, there are a number of sources of noise in the vehicle, and one of the major source of noise, especially what is called as pass-by noise, as it passes by you will hear that noise, is from the tire, right? We will sort of indicate this towards the end of the course. So it is the noise generated from the tire is what we are talking about. We'll indicate maybe in a half a class what we mean by noise towards the end of the course, but it's a separate topic by itself. Okay. You have a question?
Yes, sir. What tires do they use in 4x4 trucks?
Yeah, that's exactly what I'm saying, that what are the tires used in, there are two things here, okay. What we are talking about in those kind of trucks, we have drive axles, we have dummy axle, okay, dummy axle, and we have what is called as the steer axle, right. These are the three different types of axles you have, right. So the first rule is that, especially in Indian conditions, unfortunately many people mix tires. Like for example, they would put a nylon. Nylon is a loose colloquial term for bias tires, okay. So they'll put a bias tires and they would mix it with what is called as the radial tires, okay. It's a usual practice to put bias tires in the front and the radial tires at the rear, okay. In other words, rib tires are still not very popular in, especially in the Indian market, and they usually put a bias tire in the front, basically because rib tires are extremely sensitive to the camber of the vehicle and as well as the toe. Toe and camber has a large effect on the tire performance, and in fact, the vehicle parameters, as we would call suspension parameters, such as toe and camber, as well as what is called as the axis of thrust, okay, which we'll define later. Okay, these things have an important effect on the wear of these rib tires, and these factors usually make the tire not to wear uniformly. Okay, there would be an uneven wear in the tire. Why is it so? Quickly look at yes. So you can see the difference between, that's the contact pressure distribution when you have a camber. The camber is a very tricky business. It changes the whole contact pressure distribution, and hence it changes the way the wear takes place in these what are called as the ribs. Okay, it's a very tricky business because you have two things. One is the camber of the road. Okay, road has its own camber. Okay, maybe 1 degree. Most roads in this country has 1 degree. Okay, but it depends upon, it varies from country to country and is governed by certain standards. And you also have what is called as the vehicle camber. All of you know camber, you have studied this in your earlier classes on automotive systems. So these two combine, okay, the road camber and the vehicle camber combine. Sometimes it neutralizes, sometimes it makes it, or in sense one side it neutralizes, other side it makes it more, and so on. So this camber actually affects that's the pressure distribution. Remember last time it was such a nice symmetrical pressure distribution that you had, and the distribution is completely affected when you have a camber, and when you have a toe, then again there are differences, and the wear is not uniform in these ribs. So when the wear is not uniform in this rib, so uniformly it doesn't wear out. What I mean is that this NSDs, okay, do not go down in a uniform fashion, right? Usually what happens is one side, say one side, this side, okay, the wear may be more, and this side the wear may be less. So the tire ultimately assumes a shape something like this. Okay, so that's the groove. So that's the groove. So let's say that it would be, I'm just exaggerating it. So it would be something like this. So there's a one-sided wear, okay, one-sided uneven wear that takes place. And so the tires are usually rotated from one wheel to the other. There's what is called as a rotation plan, which the vehicle manufacturers or the tire manufacturers more importantly give you, so that it is rotated, right?
This can happen in lug tires as well, right?
Yes. Usually the lug tire, since it is at the rear, you do not have this problem. Okay, so you have a what we call a semi-lug tire, or a hybrid tire between a lug and a rib. Okay, it is something like a semi-lug tire. A typical example, I wouldn't call this, but typical example here is something like this. You have lugs as well as ribs here. Okay, a semi-lug tire is used as an all-wheel vehicle. Even there, many times you would see this kind of uneven wear. Okay, due to certain reasons which we won't be able to discuss now, the bias tires, because of the contact pressure distribution and so on, the bias tires contact pressure distribution is very different. I said that we're not going to go into the details of contact pressure distribution in a bias tire, but because of that, these tires are not very prone to the vehicle geometry, and hence people prefer to put the bias tires in the front. And when they put the bias tires at the front, their rolling resistance definitely is higher, okay, than the radial tires, and hence there is a fuel consumption which they have to pay, the penalty which they have to pay because of this factor. It's a very tricky business to actually design a rib tire with a uniform wear. Okay, the course is not on tire design, so I won't be able to. Again, sorry that I have to digress. I have to go here and there, but nevertheless, it's a very interesting and a tricky business to design a rib tire. People who are interested, the best place is to look at the patents, the number of patents that have been that are filed in rib tire design, huge numbers, which does all sorts of things in order to mitigate this problem of camber and toe. But anyway, camber and toe are reality, and they have an effect. Both of them have an effect, and it's very important that the truck owners and the guys who drive the truck, they actually look at what I would say, changes in the camber and the toe. Okay. Right. Let us come back to this. Okay, there's a lot more to that question, and anyway, a quick answer to that question is this. And the contact pressure distribution, as I said, is local bending. That's instead of understanding all these niceties inside local bending, is better to look at contact pressure distribution from a finite element analysis, which you would understand it quite well. Okay. Now, we have a lot more to cover, so let's go a bit fast. Let us understand three things: the traction, braking, and contouring before we derive simple formula in order to appreciate the physics that we are going to bring in here. Okay. One thing is very clear from what we did in the last class or the classes before, that there is a difference in velocity. Okay, a difference in velocity. What is this difference? Velocity between the tangential velocity and the ground velocity. Right? There is a difference in velocity. This is what causes deformation. Right? If the ground velocity Vx happens to be the same as that of the tangential velocity, say let's say that omega Re, okay, is equal to V, that's how we defined, and that both of them are the same. You remember that we had it at a point. Then what would happen to these tread elements? So let's say just look at this one tread element. Okay, let's say that it is rotating in such a fashion that there is no difference in the tangential velocity due to rotation, omega, versus, difference when compared to the V of the road. There is no difference. Okay, these tread elements are not going to be subjected to any force. Right? They are not going to be subject to any force. So it is this difference which is responsible for braking, traction, as well as, okay, a similar thing we would extend it for what is called as the lateral force. Okay? So it is the deformation which is responsible for all these things, and we are going to define a quantity called slip after some time. Okay? So that we understand first the physics, and then we will put this in. The difference between the tangential velocity and the velocity of the ground. Okay? So that would give rise to a quantity which we would call as slip. Okay? So we can define the slip to be, let me define it. So that's the first quantity that's of interest, what we would call as Vx. Okay? You'll see why we have put a minus there. Vx minus omega Re. That is the difference, and that's what causes the what we call as the deformation, and hence the force. Okay? That can be divided either by, or normalized either by Vx or by omega Re. Okay? Either by Vx or omega Re. Right? Okay. So let us look at what this quantity means. What happens when omega is equal to 0? What happens when omega is equal to 0? Omega is actually the angular velocity. Okay? So what is the condition? We are braking. Worst case of braking, where I have jammed the brakes and the wheel is no more rotating. Okay? In which case, what happens to that slip, maximum slip value, or a minimum value rather, because there is a minus 1. So minus 1 is the, what is the minimum value? That happens to be minus 1. right? So the braking condition, which is worse, has a slip ratio, it is a slip of -1.
Sir, they're not breaking the vehicle should stop.
Please note that when we brake, okay, we are not talking when the vehicle completely comes to a halt. When we brake, okay, we are applying the brake, jamming the brake, there has to be a force generated, okay. That's why we have F is equal to ma, okay. That force generated has to stop it, and the force is generated by these pulling. Remember that we're going to explain that again here, okay. Pulling of those bristles, okay, when they are stuck to the ground, right. That's what causes the force, because I have a wheel, okay, of a vehicle, right. Let's say that it's going in this direction. I'm going to stop it, so I have to have braking force. How do I create the braking force? Okay, so I have to, that braking force creation is what we are talking about. So we are not talking when the vehicle comes to a halt, nothing happens after that. So when I jam the brake, worst condition, my wheels stop rotating. Doesn't mean, you would have seen severe braking conditions. Doesn't mean that the vehicle immediately comes to a halt, right? So the worst condition is omega is equal to 0, okay, in which case this becomes -1. What is the other condition, the other side? The other side is the vehicle stationary, okay, and then the wheel just keeps rotating. So in other words, V is equal to 0, Vx is equal to 0. So in other words, that condition is infinity, and that is we are trying to drive the vehicle, but not able to drive it because it's not able to have what we call as a grip, right? So these are the two extreme conditions. But before we go there, let us understand the mechanics first, and we'll spend a class to understand these things from a mathematical perspective. Okay? Right.
So can you explain this again? Infinite.
Yeah, because this is equal to 0.
No, sir, what is the actual thing like? The wheel is moving.
Yeah, here the wheel is rotating. Okay, so omega is present, but there is no grip, so the vehicle is not moving. You would have seen this many times. You know, if your water wheel rotates, but the vehicle is not moving, or in sand, okay, it doesn't develop enough force for the vehicle to move, right? So that's the condition, right? Okay. Now let's now understand this and appreciate that there's a very beautiful micro mechanisms that are happening in the tire. Okay. In fact, there's a lot of, I would say, race between various quantities which decides how the tire is going to behave. Clear? Okay. Now, the first thing is pressure. We know this. I'm not going to repeat anything out of this. There's a contact pressure. Okay. The vehicle is moving in that direction, right? And there's a contact pressure. No problem. Now, let's analyze the braking condition. Let us analyze the braking condition. Let's look at that bristle, okay, which is called as brush. People call this as brush model and so on. Looks as if they are the comb, brush of the comb. So it's called as a brush model, right? Okay. There are number of these guys who are going to come and sit, and that's the ground. Let's just understand one of them, and then we'll extend it, or we will put a much larger thing. Right? Okay. Now my velocity is in this direction, so my ground velocity is in this direction. Okay. Now, ground velocity is in this direction, velocity is in this direction, but my acceleration is in this direction, right? Because I want to decelerate. So, in other words, I have to produce a force which is going to act like that. Yes?
So what do you mean by ground velocity? Ground displacement?
Yeah, that's exactly what we said in the last class, that we can have two views. One is the vehicle is moving, ground is stationary, or the ground is moving in the opposite direction and vehicle is stationary. That's what I mean. Okay. So please remember that. I'm going to repeat that again and again. Right. Okay. Now just let us concentrate on one bristle. I'm braking. Now what is the condition under this? Let's call this as the head, and that's the tail of the bristle. The head has hit the ground. Okay, and there is a contact patch pressure that's built on the head. Okay, this fellow is actually under pressure. According to what we have seen now, what is the condition? The ground, okay, the ground velocity, which is the opposite of the vehicle velocity, will it be more or less than the wheel tangential velocity? It will be more. Okay. So in other words, what would happen to this? How would this bristle look like? Okay, if you now look at the relative thing, it will be in that direction. Okay. So let me remove that. So it will be in this direction. Okay, the ground is going to run away as if it's going to run away with the head. Right, it's going to run away with the head. The leg or the tail is still sitting on the tire, on the wheel rather. Right? Okay. So what happens now? This guy is going to develop tension and is actually going to pull the wheel, and that is what we saw in one of the earlier classes, and that is going to give rise to the braking force. It's not one bristle, just to illustrate it we said this as one, but there are a number of guys who are going to participate. Okay. Now let us extend it. Let's extend from 1 to several. Right. Okay, this is the let's make it flat. Okay, so the ground is moving like that. It hits, let's say it hits, just realize the ground. So slowly it will, the number of bristles, okay, this is just for illustration we are saying this. They are now going to develop, these are the ones which are going to give you the braking force, fine. But then that force, there is also a force, this guy is not going to leave. There is going to be a equal and opposite reaction. Right? Okay. So, in other words, there is a tangential force which is generated at the interface between this bristle head, what we call this bristle head, and the ground. Right? So there's a tangential force that's generated. That's the opposite reaction. If this force overcomes the friction force, what would happen? The guy would slip. This is what we called as micro slip. I'm just repeating it so that things are clear. So he would now slip. Keep on holding. Now, as long as the ground is able to hold him, he is going to be stuck to the ground. Once the friction coefficient multiplied by the normal force that is exceeded by the tangential force, the guy is going to slip now. Okay? So at one point of time, in this race between the tangential force and the normal force, the tangential force wins, okay, the guy is going to now slip. He's got to slip. Okay. So, an oxymoron that unless there is a deformation, unless there is a slip, note this, a force is not generated. Okay? You would think that when it slips, there is no force, but actually in a tire, when there is no slip, there is no force generated, number one. Okay? When the tangential velocity and this are the same, they are not going to generate, the bristles are not going to generate the force. That's point number one. Point number two, I want to distinguish between, when I say this slips, I have just defined a slip quantity here. So what is this slip and what is this slip? So I would call this as a micro slip, right? There's a micro slip. Okay? This motion is a small motion, just this bristle just moves. Okay? Moves in such a fashion that it comes under again to an equilibrium. Okay? Now, this is what we studied before on how mu is developed. Okay. Now, yeah.
What we are talking about here is common to both rolling resistance as well as the coulombic friction?
No. We are talking about here braking force development. Rolling resistance is anyway present. Okay? Even we said even in the free rolling resistance is present and it opposes this motion. Okay. Yes. Okay. So that's a good question. How do I characterize this friction? In other words, how do I characterize this friction? Or I know that quantity called mu, which is Coulomb friction. Can I just write mu into n? Okay, is the limiting tangential force case. Is mu a constant? That's the question, right? Good question. And it's a difficult question because, strictly speaking, this is not a correct model. If you ask any researcher who works on elastomer friction, he would say this is nonsense. Okay? Because the friction coefficient depends upon, interestingly, the contact pressure P is a function of contact pressure P. It's a function of that slip velocity V, okay? Because V is proportional to omega of x, viscoelasticity, keep on building, and so on. Temperature, very important, okay, and so on. But it's a very difficult factor to take into account these things. So what people do is to follow Coulomb friction and say that the Coulomb friction, for example, for a truck tire is 0.75. Coulomb friction for a motorcycle tire is 1.02, and so on, right? So we sort of have an approximation which is not necessarily correct, but somewhere we have to start working, and hence we have to follow Coulomb friction. If you go and look at the literature, there is a number of papers on how friction is developed and so on.
Is it the same for the rolling resistance? They are also the rolling resistance.
Yeah, I said there itself that we will dump everything. We call, at that time when I gave one of the previous lectures, I said we will call this as friction, right? So the friction, as I said then itself, that viscoelasticity plays a great role, right? So pressure, velocity of slip, all those things. It gives rise to a number of other phenomena. Let's just move on. Okay, we'll look at this thing quickly. So the first thing is that there is, summarized as a race between the two. So there's a normal pressure. Okay, then there is this Fx, which is this guys pulling. Okay, so remember that these are actually different, you can view it as a different conditions also of the same bristle. With time, this same bristle goes through that kind of variation in the tangential force. Clear? So, if I now plot the tangential force variation, okay, to be something like that, I keep varying, I keep increasing, I come to a position where the normal force is no more able to sustain this tangential force. So, at that point, things are going to undergo a micro slip. When it undergoes a micro slip, okay, so again the forces start now dropping, because micro slip brings it back, the bristles brings it back, and so this elongation now reduces. So, as it happens, there is a drop in the tangential force and so on. Okay. So, that is what happens. Of course, under all these conditions, the omega Re, or in other words, what we plotted as velocity changes, okay, to similar to what we had done before, or what we had seen before. There is a compression, okay, and the compression reduces the radius, and so all those things happen like what we had seen before. So, you can interpret that from our previous free rolling condition. Okay. Now, what happens is exactly similar in the case of acceleration or traction conditions. People call this as traction whenever there is an acceleration. Okay. Now, the scene is just the other way. Okay. You are accelerating, that means that you have given the acceleration, a torque is generated, okay, the torque moves the revolves or rotates the tire faster than what the ground is moving, and hence this whole thing is the other way. Okay. The bristles are now in this direction, okay, and hence the force that is generated, remember that is the velocity, and I want the traction force to be in this direction. Now, the force that is generated is like that, pulls, okay, and so that will be a traction force. Both braking and traction force is hence generated by that difference. Okay, been telling that again and again because that is a very important concept. Right. This graph and this are exactly similar. Only thing that force directions are different. Again there is a slip, there is a micro slip, and again there is a variation of velocity and so on, right. So, that slip gives rise to a very important and interesting phenomena. Let us now look at, I think I have some slides which gives you, yes. So, that is the longitudinal force development, in braking. That is the longitudinal force development in braking, reaches a maximum, and then you see that towards the end it comes back. Okay.
Yeah. Graph, the velocity, I mean, is the velocity going to negative?
Yeah, because there will be when there is a change, velocity is not negative in sense it drops below omega or not, r. So, it is not that r becomes negative, obviously not. From omega r, what it starts, okay, it goes to omega re, and then again goes to omega r, and there is a variation in the, see, the whole thing is very simple. It is, what is the basis for this graph? What is the basis for this graph? the basis for this graph is nothing but, no, what is the basis for that graph?
What you saw there.
The basis for the graph, you remember in one of the earlier classes we said, is the compression expansion along the circumferential direction. I said, I asked you to go and lie down here, okay, and compression expansion, right? So that's exactly what is depicted here. It's not that it becomes negative, okay? Omega R naught becomes omega Re, then goes below omega R naught and then goes again up. Okay. Now, why is this very important? This is very important from one perspective. This is what gives wear to a tire. People keep there's a lot of sanctity to this, what we call as contact pressure in the tire community. Okay, looking at contact pressure, they usually say this is a good contact pressure, this is a bad contact pressure, and this gives you wear and this and that and so on. But unfortunately, they don't really understand, or I wouldn't say understand, they don't want to go into the details of how actually there is a race and there's this micro slip and there's a micro slip. The micro slip is responsible for wear, right? So there is a slip and force multiplied by that displacement that gives the work done by this friction or friction energy, which is responsible for wear. In other words, the interesting point I want you to note is that all that energy, friction energy, that is what causes friction, okay, is concentrated at the rear of the contact patch. So on either side, okay, is concentrated at the rear of the contact patch, because whatever be it, this is the reverse direction, so don't look at the right hand side, look at the left. So you would see that whatever be the condition, it is that's micro slip that causes or that gives the energy for wear, and that's responsible for wear. That's why it's very important to understand this race and understand how wear is created in a tire. Clear? Okay. Whenever these wear rates are different in different what we call as ribs or different positions, then we have uneven wear. Okay. These block tires, these tires are prone to what is called as wheel and toe wear. Heel and toe wear. These tires are prone to what are called heel and toe wear, where because of this distribution of pressure, we don't have a graph here, you would see that each block, one side of the block has one wear rate, at the other side another, and so on. So there's an uneven wear even in that blocks, which should give rise to what is called as the heel and toe wear. Okay. We will get into the maths behind it, but before that, we will explain what happens or how is force generated in cornering. Okay? How is the lateral force generated in cornering? Right? So let's say that is the lateral force that is generated. That's actually quite interesting and slightly more complex than what we have seen till now. After all, I need a centripetal force. If I corner a vehicle, I need a centripetal force. Okay? Let us say that is the centripetal force that needs to be generated. Okay? And of course, this is the D'Alembert's force, which you would call as the centrifugal force. Okay? So the centrifugal force, what does it do? It tends to push the wheel, and the centripetal force would now pull or oppose that. Okay? M omega squared R versus the F, or equal to F. Right. Let's see how this force is generated. You have to be very careful in understanding. imagine that there is also a rotation. Okay, this wheel is actually rotating. So a part of the wheel gets stuck here. Okay, so the guy, again, my good old road is going to hold it. Here he's going to hold it, right? And the wheel is now pushed out. The wheel is now pushed out, and it now rotates. Now rotates. So now what happens? If you are a material element, if you are an element sitting here, if you go and sit in a material element, and as you go now down, you are going to go towards towards the right. So as you touch the ground, okay, because these tread guys are going to sit there and they're going to be held by the ground, okay, you are going to drive a very complex path. Okay, you're going to drive a complex path. In other words, your head, which is in the ground, and your leg, which is, say, on the carcass, okay, will be like this, right? Because this guy has been pushed out, so he'll be like this, right? In other words, this inclination, which is going to increase as you travel the contact patch, as you travel inside the contact patch, gives rise to that pull, our good old pull which we saw there, and that pull results in what is called as the centripetal force. And in that whole process, the tire is completely twisted. It's just not that it's going to be in one plane. That whole process, the tire gets twisted. Right? We'll stop here and continue in the next class.